bit of stuff on chapter 7, which is a very interesting bit of stuff. Now we get to sort of wrestle with the idea of how to think about things that seem like they're contradictory, but will actually show that with a careful application of relativity, they're not contradictory. And we were discussing probably one of the most famous of these, which is called the twin paradox. And the idea is, it seems contradictory to say, from my point of view, your clock runs slow. And that means I think that you're going to experience less time between events. And from your point of view, my clock runs slow. So you would think the same thing about me. And we can't have that be true, at least in a situation where we come back together again and we actually compare things. One of us is going to be older. One of us is going to have a clock that has ticked off less time. And so here is an idea about how to do that. And the setup is called the twin paradox that we were discussing yesterday. Tara stays on Earth. Uh-oh. Always a problem. Let's see if this works here. There we go. Tara is here standing on Earth. Tara means Earth. X is a very distant place, 10 light years away. So it's going to take a long time to travel there, even at close to the speed of light. But these two places, Earth and X, are at rest with respect to each other. So they're in the same IRF. And we already know about how to compare sometimes as long as one object is present at both events. And Stella is in this rocket traveling at 0.866 c. That's conveniently chosen so that gamma is equal to 2. And so I know the times will differ by a factor of 2. That just makes mental calculations a little bit easier. So we're going to have Stella travel over there to X and immediately turn back and come back again. And of course, Tara on Earth, the Earth folks are going to say, Stella's clock was running slowly the whole time. By a factor of 2, or a factor of 1/2, if you like, right? They're slow by a factor of 1/2. And therefore, Stella is going to age exactly half the amount of time as her twin sister on Earth aged. And we should be able to see that just by how much time is ticked off on clocks on there, too. And that's true both on the way out. Stella's clock is running slow on the way out, and it's running slow on the way back as assessed by Earth because she's moving at the same speed relative to Earth. Okay, that sounds fine. Clocks on the rocket run slow, so Stella ages less. That's the Earth statement. But from Stella's point of view, on the way out, Earth and X are moving relative to her, and so their clocks are running slow. And they're also running slowly on the way back when Earth and X reverse directions, at least, after she feels those inertial effects of actually turning around. Earth and X are still moving, and so they're ticking off slowly. And so she might think the clocks on Earth run slowly, so Tara ages less, and it seems contradictory. In this case, the situation is not symmetric, and that comes. The only place where the lack of symmetry comes in is at that turnaround point. When Stella reaches X and turns around, we're going to find something drastic happens there. And we already saw a prelude of that in the previous worksheet, where we saw the assessment of the time on Earth really changed a lot at the point of view where someone turns around and starts going in the other direction. Okay. So we said, here is the setup. Just I was rushing a little bit at the end of class yesterday, and I'm just going to go through this as a group. But if you don't understand something, please stop me, and we can talk about any particular reading here. Earth and X being in the same inertial reference frame, of course, they synchronize their clocks. And they decide when Stella leaves Earth, we're just going to set our clocks at 0. And the person on the rocket, Stella, also says, well, when I leave Earth, I'm just going to set my clock at 0 years, and we'll have our clocks tick off in years. So everybody agrees to have their clocks read 0 at the instant when the rocket leaves Earth. So this is an event here. Okay, so from the Earth's point of view, by definition, they look up at the rocket, they say the rocket's clock read 0, and we have carefully set our clocks to read 0 at this event, rocket leaves Earth. What are the assessment of the rocket clock the Earth clock and the clock on X's reading as the rocket first leaves Earth from the point of view of the rocket IRF as it's going right, in other words, towards X. The rocket left IRF doesn't make any sense here because at this point, at the time of this event, the rocket's purely moving right. So what did we say about the rocket reading here and the Earth reading here? What do those have to read? They have to read 0. That was the principle of invariance of coincidences. There's a coincidence of rocket leaving Earth and, for example, rocket clock reading 0. Those are two different descriptions of an event that happened at the same place and the same time, and therefore all IRFs are going to agree on the outcome, and therefore the rocket and Earth clocks both read the same thing in any other reference frame, including the one involving the rocket going to the right. The assessment of the time on X as assessed by the rocket is not the same as the time on X when the rocket leaves Earth as assessed by Earthlings. Those are different, and that's because all of a sudden you're leaving Earth, you look over at X, I'm heading to these two events, the rocket leaving Earth is simultaneous in the frame where those two things are at rest, and then if we start moving with respect to there, the one we're heading toward happens first. So if I'm here at now on Earth, leaving Earth, I'm heading toward one that happened first, but here it is now, it happened before this, so it's in my past. The rocket leaving Earth is in the past, and the difference in the clock readings is given by LV over c squared. And so the clock that we're heading toward is always going to be ahead. So it's already ticked off to 8.66 years at this point. So just by changing the IRF you're in, your assessment of the time at a different location changes drastically. So this 8.66 here is LV over c squared, where L is 10 light years, LV over c squared. V is 0.866c, and you can just calculate it. It's 8.66. All right, so there's one event described from two different IRFs. Now we're going to do the same thing after this traveling is over. The rocket arrives at X, or it's just about to arrive, so it's still moving to the right, but it's there arriving at X, but still moving to the right. How do we get these answers in here? There's just, sometimes there's not too much work to be done, but there are some calculations. How about the Earth's assessment of the time on Earth clock when the rocket arrives at X? How could I calculate that 11.5 years there? In other words, you're sitting here on Earth and you're saying, how long am I expecting my clock to tick off as this thing goes at 8.866c in that direction for a distance of 10 light years? Yeah. Yeah, distance equals speed times time. The distance you're going, again, here we're doing it from the point of view of the Earth reference frame. So the Earthlings are saying it's a distance of 10 light years. We're not moving with respect to these. Of course, Stella is going to say it's length contracted, the distance between Earth and X. But from the Earth point of view, the rocket has to go 10 light years, and that's equal to the speed they're going at, 0.866c times time, and you can solve for time, and that's just 11.5 years. That's what Earth says its clock will read when they arrive there. Well, Earth's clock, in the Earth IRF, Earth's clock is synchronized with the X clock. That was the whole part of the design of this. Because they're at rest with respect to each other, we want them synchronized. So these two columns right here should always read the same thing. That just means that from the Earth IRF point of view, the time on Earth and the time on X should be the same reading at the same time. We synchronize those clocks, they're going to tick off at the same rate, so we don't expect them to ever disagree. How about this 5.77 here? Earth is assessing what the time on the rocket clock is when it arrives there. How would I get that from the number I just calculated? All right. It's the time dilation, right? When someone is going between two events and they're present at those two events. That was the one case where we could just simply use the time dilation. Stella is present at the two events, and we said Earth is assessing it took 11.5 years, and so Stella is going to have the smaller of those according to the time dilation. So that's the time that Earth gets divided by gamma, or we divide by 2. So 11.5 divided by 2, 5.77. Okay, why does the rocket clock, when the rocket arrives at X, why does the rocket assess that its clock reading when it reaches X is the same clock reading that Earth assesses when the rocket reaches X? Yeah. Yes, well, so that's certainly one way to do it. I was going to say the principle of invariance of coincidences. In other words, rocket, but you could do it that way using the shorter distance that the rocket has there, and you're going to end up getting the same thing. So Jack was saying distance equals speed times time. That's one way to think of it. But another way to think of it is, look, the rocket arriving at X is some publicly identifiable thing, which is coincident with the rocket's clock reading being 5.77 years. Doesn't matter who's looking at it, that we all have to agree that the arrival of the rocket and the reading on that clock are the same from the point of view of every reference frame. You can see there's a lot of subtle thinking here. Although none of the calculations are hard, you have to keep switching and thinking about what can I rely on? All right, what about from the rocket's point of view, when the rocket arrives at, let's try to do the simpler one here. When the rocket arrives at X, what is the clock reading that's at rest on X going to be? 11.5. Where's that 11.5 coming from? When you say that, that probably may make sense, but I was thinking of an even simpler explanation than that from the principle of invariance of coincidences. Just like we concluded that the rocket clock, when it arrives at X, has to read the same from anyone's IRF's point of view, because it's coincident, the rocket arrival and the clock reading there are publicly identifiable kinds of things. It's the same thing with the X clock reading. We already decided that the X clock reading from the point of Earth being 11.5 was coincident with the rocket arriving at X. The rocket's got to agree with that too. So one easy way to think of that is those two have to be the same, because there's an arrival and there's a clock reading, and they're happening at the same place and the same time in one IRF. That means in any other IRF, it's just, a no-brainer there. Okay, what about the rocket's assessment of the time on Earth when they arrive? I'm looking at Everett because I think he has the right idea of how to get to that 2.84 there. Yes, so you could do half of 5.77. Often there's several ways to think about it. I was actually thinking about it as, look, I know the time, the Earth and the X clocks here are moving with respect to the rocket point of view, and the one I'm heading towards, which is X, is going to be the one that's ahead. So if I want to know what's back there on Earth, I need to subtract off an LV over c squared. And that LV over c squared, we already calculated up here, is 8.66. So if I take the reading on X, which we've already figured out, and subtract off LV over c squared, that's the difference in time readings, we get the one that hasn't ticked off as much time. In other words, it happens later. The one we're heading away from happens later. Whew, okay, I know that's a lot of work just to get a few numbers here, but each one is not a hard calculation. We've already done all the calculating we really need to do other than adding and subtracting. Let me put the rest of the numbers in here, and let's think about now, just, according to someone in the rocket or someone present at X, it's almost the same event. The rocket's arriving at X, and the rocket leaves X going in the other direction. So as long as you're at X, those are really the same event. How is that going to inform what I'm seeing here on Earth as the Earth's assessment of the time on the rocket clock, the Earth clock, and the X clock? Why are they all exactly the same as they were on the line above? Yeah, they leave right when they get there, so the getting there moment is the same as the leaving moment, right? There's no difference. And so from the Earth point of view, these are exactly the same. Now, I can't make the same argument for the rocket right IRF. That's the rocket where it's heading towards X, because suddenly it's changed IRF. So we can't just immediately copy this down here because there isn't any relevant rocket going to the right anymore. There's a rocket now heading to the left, heading back to Earth, or Earth is heading towards it. Help me just figure out where these numbers come from. Why is the 5.77, the rocket assessment, the rocket as it's going left assessment of its own time, the same as the assessment of the time that Earth makes for the time on the rocket? Yeah, there are several ways to calculate it probably, but the invariance of coincidence is the easiest way to calculate it. The rocket leaving X is a publicly identifiable event, and its clock reading is a coincident event, and so every IRF should agree on it. We already figured out what it was supposed to be here, and therefore it's the same. Same thing applies to the reading on X, right? The clock reading on X is something that's coincident with the rocket leaving X, and therefore, because Earth assessed it to be 11.5, I've already forgotten how we reasoned through all this, but we got an 11.5 there. It's got to be the same as the 11.5 over here. Now, this number, where am I getting the 20.2? All of a sudden, we're trying to figure out if the clock on X reads 11.5 when I leave going to the left. How would I figure out what the clock on Earth, which is moving with the clock on X, should read? In this case, it's not multiplying by gamma because 2 times 11.5 would be 23. So that seemed hopeful, but it's not quite there. Well, again, Earth and X clocks are simultaneous in the Earth and X frame. In the frame where the rocket is moving to the left, those things are going to the right relative to it, right? So they're seeing Earth and X now going in this direction. We're heading towards Earth. Those clocks are synchronized in the other frame. I'm heading towards Earth, and that's the one that always happens. The event I'm heading towards, which is the arrival event, happens first, which means, sorry, not the arrival event, but the event on Earth that corresponds or is at the same time as me leaving X, right? I'm looking at an event way over here, and that one's going to happen first. Now for me is later, right? So in this case, that one that I'm heading toward is actually going to have happened first, and therefore it has ticked off, or it's going to be 8.66 LV over c squared ahead of the clock at X in that case. In other words, the difference between these two clocks that are co-moving is just LV over c squared, right? The one you're heading toward is ahead, so we just add that same 8.66 onto the 11.5. Okay. Whew, I'm getting tired of all these numbers so far, but let's figure out where the final numbers go in the row here. Rocket arrives at Earth. Let's first talk about the 23.1 that appears in both of these locations. We said they always have to agree because in the Earth's frame, these two clocks are synchronized. But where's the 23.1 coming from? That sounds like a number that I think Joseph just tried to get us to calculate a moment earlier. And it is, well, look, Earth is saying it took 11.5 years for you to travel over there. Of course, it's going to take 11.5 years for you to travel back. So I just double the 11.5, right? I do a distance equals speed times time from the point of view of the Earth, and I get 11.5 again. So I just add that onto the time it read before, and it's 23.1. Okay, what about the rocket arriving at Earth? Where is this 11.5 coming from? Well, I knew, let's see. I knew my assessment when the rocket left X and started heading. Its clock read 5.77. It's heading to Earth. Its clock is running slowly by a factor of 2, and I can count on that in the time dilation sense because the rocket is a thing present at both the leaving and arrival thing. So whatever time I think it took, the rocket should assess that it takes half of that to travel it back again. And that means we just take 5.77 and divide by, multiply by 2. We get another 5.77 that's being ticked off on the rocket's clock in between those two events. Okay, and finally, the same event, rockets arriving at Earth, what does the rocket assess its clocks as reading? The 11.5 here, I think we could get from the principle of invariance of coincidences with this one over here. The 11.5 because the rocket's arriving at Earth and its clock is reading a certain thing at the same time, so all IRFs should agree on that. The same thing with the Earth's clock. They should agree in those two locations. Uh-oh, that's always a bad sign when that happens. Better click on here so I don't start messing things up. So that 23.1 on Earth is is a reading on Earth when the rocket arrives. So that's two coincident events. Everyone should agree on that. And how about the rockets? This is really kind of an unimportant or uninteresting number here, but how would I figure out the rocket's assessment of what the time is on X as I'm just coming into Earth at gamma equals 2? I haven't slowed down yet. What's the time on X when I arrive at Earth? Well, I know the clock on Earth is reading 23.1, so it seems like I have to subtract off LV over C squared. Is that a no? Oh, yeah. In other words, these two clocks are moving from the rocket's point of view. They're synchronized in the other frame, and so they're asynchronous by LV over C squared. And so I need to subtract off that 8.66 to get 14.4. That's not the most interesting number. The most interesting numbers on here are by far, look at when the rocket switches around. It goes from the rocket right IRF to a moment later to the rocket left IRF. And look at what its assessment of the time on Earth is that changes. Just before stopping and turning around, it said the time on Earth was 2.84 years later. Just after it turns around, its assessment of the time on Earth is 20.2 years later. So all of a sudden, everyone, from their assessment, they don't have any direct knowledge of it, but indirectly from using the idea of simultaneity, they have assessed that everyone on Earth suddenly aged by, whatever it is. I got to look at the numbers. One's close to 3 and one's close to 20, so about 17 years, right? Everyone aged by about 17 years just by going like this. That's what I was trying to indicate to you with that little thing with the man running one way and the other. There's something that sounds absurd about that. Someone died on X, and here I am at Earth, and I would say, now they're alive. Now they're dead. Now they're alive. Now they're dead, just by going back and forth like that and changing my IRF. It's the same way here. But that is it is that asymmetry, that turning around and going from right to left, that actually determines that the twin paradox is not symmetric between the two things. And in fact, the traveler actually is younger by a factor of 1/2. Right, has aged by half the number of years in that case. So, the rocket has aged by, when the rocket arrives at Earth, The Earth clock reads 23.1 and the rocket clock reads half of that, 11.5. So that's the twin paradox in sort of excruciating detail, you might say. Can I answer any questions on that? That's probably numerical overload. Many of these numbers are not difficult, but just the brain power it takes to think about each one of these and what might be coincident with it, or whether I'm thinking of a clock that's ahead or behind, or whether I'm using distance equals speed times time. Those are the only three concepts we use to fill out this entire thing. But the key thing I wanted to point out here is, as the rocket changes directions, their assessment of what time it is on Earth right now goes up dramatically. And that's an example of the conventional nature of what time it is now at a distant location is. It's the best definition we can give, but it is still a definition, and it leads to some things that sound kind of funny. Now, they have no consequence because I'm not directly, right now, influenced by something that's very far away. There's no way for whether someone's still alive or dead on a planet far away to affect me right here. So it doesn't lead to any logical contradictions. Questions on that before we go to a couple other qualitative paradoxes, which won't take quite as much calculation. These are to point out that you can really confuse yourself. Start thinking about the symmetry between different points of view. So here's one that is called the garage paradox. There are other names for it, but this is one I just found pictures of on the web, so I grabbed it from somebody else's site. Imagine a car that fits perfectly into a garage with the front and back doors sort of closed. So we're going to imagine there's a back door here that can be swung open or closed, and same thing on the front. And the car is the exact same length as the garage when they're both sitting at rest with respect to each other. So it just barely fits in the garage, okay? And there are three garage attendants here. A understands something about relativity and wants to demonstrate the length contraction to his partners B and C. And they agree on an experiment where C is going to get into the car and drive through the garage at gamma equals 2, 0.866 C. Okay, ridiculous, but still in principle, something we can imagine. And the idea is, at first, we're only going to have the back door of the garage open. The front door will be shut, okay? The car is going to be length contracted, says garage attendant A, and therefore, we can close the back door and only then open the front door, and we'll be sure that the car was inside the garage. Okay, and that's going to be an indication that the length contraction works. In other words, A is going to stand at the back door. That's originally open. B stands at the front door. It's originally closed. When the car comes in, attendant A, as soon as the bumper passes the back door, A shuts the back door. And then, just so we don't have to wait for a signal there, maybe we can actually time when that's supposed to happen. And at that same instant, B is going to open the front door. So the car has to be contained in between those two. I'm phrasing it as if they're simultaneous events. You actually have some extra time here, right? You would say you could just close it and then wait 1 nanosecond and then open the front door. But it'll be easier to think about if we think of them as simultaneous. Okay? Now, the problem is C is convinced by A's conviction and starts driving toward it, and all of a sudden gets very worried about the experiment. And why is that? What's C going to see if we imagine seeing, of course, really this involves a whole bunch of people in your IRF taking careful measurements, but if we imagine, that's why I put C in scare quotes here. They're not going to really get to see it with their eye, but if they had people moving with them, what would they determine about the situation, what the situation would look like if we put all that data together? What's that? No, A is going to be open. Everett. Yes, from C's point of view, the car is this length up here, but the garage is shrunken. So it looks like this. And that is not looking good. And so the question is, suppose A and B dutifully do their things. They say, I'm going to wait till the back bumper of the car passes the back door, then I'll shut the back door. I have my, I determine what time that's going to happen at exactly because I know what speed this thing's going at and when it left. And I'm going to have B synchronize his or her watch in there, and at that same time, they're going to throw the door open. And you look at it from the point of view of C, and you say, well, that's hopeless. The back door definitely has to be open before the front door is closed there, right? And that's not the plan. And so the question is, if A and B do as they're attempting to do, close the back door just before opening the front, what's going to happen? In particular, what is C going to see happen? Anybody have any ideas how to think about this? Yeah. Yes, so I'm just going to try to repeat what Jack is saying for the benefit of those on Zoom. From C's perspective, B is further on down the line than A as they're approaching, yes?
So as C drives up, C sees B open the back door before A closes the front.
Yeah, so the claim is, even though the events of opening the front door and closing the back door are simultaneous in the garage reference frame, I'm just rephrasing, I think, what Jack says. From the point of view of C, they're not going to be simultaneous events. And which one's going to happen first? Well, we know it's the one you're always heading toward. So even though these happen at the same time in the garage frame, from C's frame, B is going to happen first, the opening of the back door, and then the closing of, the opening of the front door, and then the closing of the back door. I'm not really sure which one's the front and the back, but the one by the back of the car. Here's another way to think of it. Imagine that we're going to watch a car go by, this car go by, and we're going to have people standing right where the front and the back bumpers will be, including the length contraction, and we're going to simultaneously plant some flags there where the front and back bumper are at an instant in time, right? And what is the car inertial reference frame going to see? Well, the car, of course, thinks it's at rest. It's not length contracted, right? The distance between the flags is length contracted, and they see the flags flying towards them. And as Jack just pointed out, that first flag is going to be planted first. The second one can't be planted there by the principle of invariance of coincidences. It has to be planted by the back bumper. So this car sees this one get planted first. Even though they're simultaneous in the earth frame, from the car frame, this one gets planted first, and then, oops, only later does the one by the back bumper get planted. And notice, principle of invariance of coincidences is not violated. The planting of the flag and the car bumper arriving at that location are the same in both reference frames that we're considering here. And the same thing for the back bumper and that flag being planted. It's just that they don't happen to be at the same time. Even though both coincidences apply, they're not happening at the same time as assessed in different reference frames. Okay, so in the car's reference frame, as Jack noted, and please raise a question if you're not seeing why this is true. The front door is open, thankfully, so you can let the front stick out, and only later is the back door closed. Okay, so that's a qualitative kind of explanation of how to think about something that seems paradoxical. You'll see sometimes when I write the word paradox, I put paradox in scare quotes because it's not really a paradox. There are no paradoxes in special relativity. There's only a misapplication or misunderstanding or a partial understanding of the results, right? Here, the person thinking about it is understanding the length contraction, but they're not also understanding the relativity of simultaneity. Okay, let me just show one other sort of qualitative one. Although there's some numbers ticking off on clocks, it'll be made easy by the fact that, so here's Einstein standing by a platform with a whole bunch of clocks, and there's another clock going by. They're all perfectly well-functioning clocks. It's going by at gamma equals 2 to make our mental calculations easier. And suppose we all observe that when this clock passes the first clock on the platform, it reads 0. Maybe it's in seconds, okay? The question here is, Of course, we're going to take, so what we're doing is we're sitting at rest with respect to the platform. We're Einstein here, sitting at rest on the platform. We see this thing flying by. All these clocks are synchronized and they're ticking in lockstep. When it's moved 2 down the line and this clock reads 8, what is the one up here going to read? I have this phrased as a voting question, but we don't have to vote on it. You can just shout out what you think the answer should be from the results that we've talked about, in particular with the time dilation. Hint, hint. I'll give you a hint. It's not none of the above. That's a lot of information because there were a lot of things I didn't put up there. What was that? 4, did you say? Yes, 4. You know, Einstein's saying that this clock that's moving along is ticking off at half the rate. So if they both read 0 here, and I can think of this as 2 events happening, right? The flying clock passes the first clock is one event, and the flying clock passes the third clock is the second event that we're talking about here. And so those are 2 events. The flying clock is passing between them, and so I can safely apply that time dilation formula from the point of view of someone on the platform who thinks that this thing is moving and saying they're going to experience less time, or it will tick off less time. So the answer is it reads 4 there. Okay, what about it when it moves twice as far down the line? Not a 2 clock distance, but a 4 clock distance. When this one below it now, of course, it's going to take twice as much time to get from there to there as it compared to all the way to here. So these clocks have ticked off twice as much time as they had up there. What is this clock going to read there? Not a trick question. Jack's sort of gesturing, but I didn't hear a number. 8, yes, it's gonna read 8, just same reasoning as before, right? Here's an event, these 2 passing. Here's another event. This clock is traveling between those 2 events, and so we can safely apply just the time dilation in one direction because the same clock was present. And the takeaway message we always remember is the clock that's moving between the events experiences less time, and so it's going to tick off only half the amount, right? So it gets down here, it's 12. Okay, got that figured out. The moving clock runs at half the speed of the clocks on the platform, and therefore the time measurements by the moving clock between events will be less. But, and yet, from the moving clock rest inertial reference frame, we're about to sit with the moving clock and see the platform moving with respect to us. So we're going to pretend the moving clock is at rest. Here's the same paradox we keep addressing. The platform is going to be the set of clocks that's moving slowly, right? So shouldn't the platform clocks measure the shorter time between events? How is that going to work? Well, let's take that point of view, okay? I'm just putting this in a little blue box over here. This is what we just found out from the other IRF's point of view. But now we're going to stand with Einstein. Here we are sitting with this clock. We feel like we're perfectly at rest, and the platform's moving by us in the other direction. Now, given what we found out in this other case, or what we said happens here, what does this clock here have to read? 0, right? Principle of invariance of coincidences. 2 different IRFs seeing the same coincidence happening there. Now, here is a question that takes a little bit of thought. What does this clock have to read as the 4 passes over it? Well, this one doesn't require too much. I'm thinking ahead to the next question I'm going to ask. This one's not too bad. Well, it's either 2 or 8, it seems like, but I've already got some evidence for the 8 down here. Notice, this is a coincidence that was seen in one frame, 4 above, 8 below. So when 4 is above, it's got to be 8 below. That's principle of invariance of coincidences, right? Clock passing and the 2 clock readings are all a coincidence of 3 events. Everybody's going to agree on those coincidences because they happened at the same moment at the same location, regardless of your IRF. Okay, so that one's still going to be 8. And of course, when it passes the third one, the one below will be 16, and then all was half. That seems a little bit strange, but let's keep thinking about this. I want to fill in some of these other clock readings here. And here's the one I was thinking of that's perhaps difficult. What does this clock have to read right here at the instant where the front clock is passing the one that we are now imagining sitting at rest? Now, let me phrase it in a way that's suggestive. From the point of view of Einstein, which we're taking here, how much time ticks off on each one of these clocks between this picture and the one down below? Each one of the platform clocks has to tick off how much time? Well, Einstein's clock, which is sitting at rest from his point of view, ticks off 4. The platform clocks are moving, so they have got to tick off how much time? 2. That's the time to, I know everybody's hesitant because they're so easily duped by all these things. You can easily think of them backwards. But the more you practice with this, the more it will, the less likely you'll be to be duped. That's not to say we'll get to 0, but at least we can reduce the amount of times that you'll be duped by these kinds of things. So here's the same clock, the third one down. Here's the same clock, third one down. It's got to read 8, and it's going to elapse by 2 seconds. So what does it have to read in the upper frame there, the question mark? 6, of course, right? It's going to elapse by 2. So that one reads 6. And of course, I know if there's a certain asynchronousness between clocks that were synchronized in their own rest frame, but now they're not synchronous in a frame where they're seen as moving, right? In this case, if we have the distance between the two, we're going to have the time that they read by as much too, right? In other words, if I have a bunch of clocks that are all synchronized and then I watch them move, the one that's half the distance from another one, if I know that other one's reading, it's got to be halfway in between. In other words, they sort of go, the amount of asynchrony increases as you go out. So that one's going to be 3. So they go up at each instant in time, where instant is defined by Einstein here, who's sitting with the clock that was formerly moving. As we go down the row, each one's going to increase by 3 seconds, or 3, whatever a tick means here, right? Now I can fill in all the other ones down here, because I know all of these, according to Einstein, are ticking off 2 extra seconds between each frame as we go down, right? Because Einstein's clock is ticking off 4. These are moving slowly, so they've got to be ticking off 2. And so we can fill in all the numbers there. They're all ticking in lockstep, but according to Einstein, they're ticking slowly by a factor of 1/2, right? Okay, now to sort of summarize how to think about this, the clocks on the moving platform we see they're actually running, each one of them, at half the speed of this observer who's moving with this clock up there. And yet the time between events adjacent to Einstein is double on the platform. Notice, Einstein says, here's an event, this clock reads 0, this clock reads 0. Here's an event, the upper clock reads 4, and the lower clock reads 8. So it seems like the time between those events is actually going to be assessed to be double by someone who's sitting with, in either case, the effect is going to go the same way. The platform is going to assess more time between those events, and Einstein is going to assess less time between events. That's because of the asynchrony between these clocks when they're moving like this, as much as it is about the time dilation. So notice, again, they're still ticking at half the speed, but because of the way they're asynchronous with each other, they just combine together to make it, everyone's going to agree that the time between this event where these 2 clocks line up and this event where these 2 clocks line up is going to be assessed to be half by the person who's with the single clock as opposed to the other ones on the moving platform. Whew, that was questions on that. I'm trying to say the same thing several different ways. So the garage paradox is one way of thinking of it. The twin paradox is kind of in a different point of view, because here we're not switching reference frames and turning around ever. So these are kind of simpler paradoxes because they're only comparing 2 different ones. Whereas in the twin paradox, in order to break the symmetry, we had to switch to a third one. Jesse? The question was, if we didn't know that if we didn't have this blue box, if we hadn't already done the analysis right here, and so we didn't know that this clock had to be 8 by the principle of invariance of coincidences by comparing with the blue box over there, would we think that we should really have a 2 there? And the answer is, well, no, not necessarily, because here this 0 is next to the first clock, and here this 4 is next to the third clock. So in one case, there's no guarantee that the displacement in time between the first clock in one frame and the third clock in another frame, they're different clocks at different locations, that they should be different by 2. What should be true is that the same clock between these frames, like the fourth one, should be ticking off by 2 seconds from 9 to 11 there, right? That's certainly true. But when we compare different clocks, they're in different locations and they're asynchronous. So we can't rely on the fact that just because all the clocks are running slowly, that the difference in time between the first one and the third one is 2 between the frames, because we have to take into account how much the time is staggered as you go on down the line. I know it's complicated, but the more we work with it, and we're going to sit on this for a while, the next 3 or so chapters that you're going to continue reading, just digest it. Merman brings up objections, and then he tries to relieve you of those objections. Some of the objections we've already addressed in the way I've presented it. This busy slide I'm not going to go through, but I'm actually going to pass it out to those of you here in class. It just summarizes these 3 effects. Each effect we've sort of said in 2 different ways, right? Time dilation, we said moving clocks run slowly, but then there was also a specific case where we could apply it to the time difference between events, where one frame happened to be present at both events. Similarly, for length contraction, there were kind of 2 different presentations of it. And now you've seen the relativity of simultaneity. There is a clock asynchrony version, and then there's also the how long you have to wait version of it. They're not too different from each other, but I wanted to make sure you had them all in one place. For those of you on Zoom, I am going to post this in the middle column on the website so that you can print it out if you like. All right, that brings us to just about the end of what I wanted to talk about. The remaining thing, I think, is your reading responses. Very interesting comments. I got a thumbs up there from Jacob, thank you. Very interesting questions on the reading responses, and a lot of you mentioned that this was really a highly technical chapter. Hopefully the presentation we did in class, at least if you want more details, you can go back and watch the videos. For those of you here in class, the Zoom folks know probably, but I post the videos from the class every day after lecture's over. So sort of by the end of the day, it should be up on the website. So if you ever want to go back and look at those, inspect the slides. If they were flipped through too quickly, you can watch them again and pause them at any point. Okay, so let's look at some chapter 7 reading responses. Why does moving perpendicular or parallel change when the clock would be viewed as slower than the one in the back? I can only just sort of think about what is being thought of here, but the idea is we're considering 2 clocks maybe attached by a bar, and we're either going to consider from the point of view they're synchronized in their own rest frame. We're either going to move along the direction of the bar or perpendicular to the bar. And the question is, why would that change whether the clock would be viewed slower than the one in the back? And the idea is, well, first of all, there's a little bit of a language here. Maybe this is just me reading the meaning incorrectly. It's not that we're, so I imagine these 2 clocks from the point of view that they're moving toward me on a train or a bus or something like that. The one in the back is not going slower. It has, the one in the back happens first, so it's going to have a later reading, right? The reading on the clock is going to be later by LV over C squared, where L is the proper distance. So I think I put this up here just as a cautionary thing. It's going to be slower in the case where we're moving along it, Whereas in the direction, if we move in the direction perpendicular to the displacement between the clocks, we actually found out that there's no effect. If they're synchronized in the rest frame, they're synchronized when you're moving in the direction perpendicular to their displacement. But in neither of those cases is either clock running slower than the other one. Both of them run slow compared to a clock that they're being compared with someone who's watching it go by. But neither one runs slower than the other if we consider the one in the front or the back. This second comment is sort of the same kind of thing, and I think this was someone thinking through this language. Usually the one in the back is slower. No, the one in the back is not slower. It has a different time reading, but it's ticking off as the same rate as the one in the front. Maybe if we think something's behind, maybe it's behind because it's slower, right? The race between the rabbit and the tortoise and the hare. The tortoise is behind because it's slower. But in this case, that's not true, right? We're watching a train go by, and the back and the front are moving at the same speed. So they're going at the same rate, and that means their clocks are going to be time dilated by the same factor. Here was something that several people brought up. These two kind of go together in the middle here. I was wondering if this idea contradicts the principle of invariance of coincidences, because it creates different times in different IRFs. So if the car were to crash at a certain time on the faster clock, that event would have already happened when the slower clock reaches the same time. The person down below, something sympathetic. I'm wondering how we explain the principle of invariance of coincidences with these new rules. The car crash example is especially bugging me now. Let me switch to the camera. So I'm going to unshare my screen here. I've got to fix the camera, but let me just draw a picture. Let's imagine two car crashes. Let's imagine, this is a real tragedy of a day in Danville, Kentucky. Here is an intersection. Here's another intersection. At this intersection, a red car and a blue car collide. And from the point of view of someone on Earth, in the Earth reference frame, right? Of course, Earth, again, isn't an inertial reference frame, but we can take a small patch of Earth, and it's approximately moving at a constant velocity, even though we know if you wait a whole day, you are actually turning in a circle, so it's slightly non-inertial. But this patch of Earth is very, very close to an inertial reference frame. So according to people standing at rest on Earth in Danville, Kentucky, red and a blue car collide here at the same time. They crash, so we can observe that later on. At the same time, a yellow and a green car. When I say same time, I mean according to Danville people, just standing still, not moving at close to the speed of light relative to Danville. Red and a green car crash over here. Let's take the point of view of someone in a rocket heading, it looks kind of like a carrot, but it's a rocket heading to the right at very close to the speed of light. How are they going to assess those two things? Are they going to disagree about whether a crash took place? No. What are they going to disagree with? The statement of that these two crashes happened at the same time. They're going to say that the green car crashed with the yellow car first, because whichever event you're heading towards, that's one of our mnemonics, in the frame where you view it, the two events. The two events are simultaneous. If I view it from the point of view where the events are simultaneous, whichever direction that other frame we're about to consider is heading towards, that's the one that happens first. So the yellow car and the green car crash first, and then according to their IRF measuring folks, this red and blue car crash a little bit later. But at no point does either of those coincidences not happen in the same way. It's just that their displacement in time might be different. If you switch the direction you're moving at, you're instead going in this one, then the red and the blue car would crash first. And then later on, the yellow and the green car would crash. But all the consequences that follow from those crashes would still happen in the same way, regardless of which order you saw them happen in. Yes, Emily. Yeah, so there's some question about that Emily is asking about causality. Do they have to be sufficiently far apart that they can't affect each other? And the idea is, of course, how far in time that this moving frame sees these two be apart when they're simultaneous in the Earth frame, for example. How far in time that these two differ by from this depends on two things. Not only how far apart they are, that we're talking about the LV over c squared times that gamma factor is the one, is how long we have to wait between the two. They depend on L between these two, but they also depend on the speed that you're moving at. And the bigger the L, the greater the difference in time. So when these two events start to happen really close to each other, the time difference between them by someone going at the same speed is going to get smaller and smaller. And it goes to zero as the locations get closer and closer. And since it goes to zero as we bring those two intersections close together, they would approach the same coincidence, right? And so everybody would have to agree on it. And so in that case, the time difference, if we brought these two intersections closer and closer together, this person would say, oh, there's zero time difference between them. Well, there's got to be, because they're a coincidence at that point. They happen at the same place and the same time. So it all kind of works away. So the farther away two events are when they happen simultaneously in one frame, then when viewed from a different frame, the greater the difference in time between those two. One's going to happen much earlier than the other one, but the chances of them being able to causally affect each other are just as remote there, because any information, if you're going to say, send a signal back, and we will address this at great length later on in Merman. Send a signal back so that when it gets here, you turn all the lights red and we avoid the crash or something like that. This one happens first and this one happens later. We're going to find out that even if that signal is traveling at the speed of light, the fastest speed that we're going to be able to send a signal at, it won't make it there in time. So if they can't causally affect each other in one point of view, they can't causally affect each other in any other one. So whatever happens, happens in both cases, regardless of if one happens first, you try your hardest. And of course, it's in vain, because if one happens first from this point of view, you just switch the direction of the rocket and they happen in the reverse order. So how could the person possibly stop it? And there's all sorts of interesting consequences associated with that, like time travel things. People saying, okay, well, if mine happens first, I'm going to try to go back and kill my grandmother so that I never get born, and what's going to happen there? We'll address that in great detail several chapters down the line. Any more on that one? There was several mentions of the principle of invariance of coincidences. Oh, I'm going longer than I said I was going to today, but very interesting stuff. Last two here. I find it pretty unsatisfying that Merman only focuses on what happens when an observer moves parallel or perpendicular to the line connecting the two clocks. When there are an infinite number of other angles an observer could be moving along, it feels as if we're only learning about very niche scenarios at the moment. And that seems to be the case, but we'll find out just in the same way that we said, once we know the parallel and perpendicular length contraction case, we know all the cases. We could figure out how an astronaut with a weird shape moves, is deformed when you move in any direction with respect to that astronaut, and you did something like that on the Chapter 6 homework. It's the same way here. Let me just draw a little picture. So I think the idea is, well, let's suppose we've got, a bar connecting, two clocks that look like this. This is the way I've been drawing them, right? And we're going to imagine, someone in their rocket moving in this direction. I think that's the kind of scenario this person's saying, Merman dropped the ball on this, right? We didn't address this scenario. Can anybody see how to use the information that we have just for the parallel and perpendicular cases to see from this person's point of view, if we imagine them at rest and this thing moving by in that direction, slanted, of course. It might be slanted at a different angle because the length contraction only slants it, only compresses it along the direction they're moving, but still it's going to be at an angle in this person's rest frame. How we could figure out, what the difference in the time readings of those clocks are, for example. Well, it's getting close to the end, so what I'm going to do is just kind of tell you how we might think about it. I'm going to make this into a triangular piece, right? And I'm going to imagine there's another clock down here. Okay, so there's three rigidly connected clocks. if we're going to compare, so let's suppose we synchronize all three of these clocks in their rest frame. And then we ask from this person's point of view, if this clock reads 12 noon at a certain instant in time, what's this clock going to read? 12 noon, right? That's using the perpendicular rule because that's a displacement perpendicular to the direction they're moving. And how about the displacement in time between these two? Well, I would need to know the L between these in the proper frame, but these two are going to be asynchronous from each other. So I can move along a diagonal by just successively applying the parallel and perpendicular kinds of rules. So Merman really, maybe he doesn't make a good enough impression about how this is the case, but he's really done everything there is to be done other than explain how to put the two together. And maybe he did drop the ball on doing that explanation, but there's nothing missing here. Sorry, one more reading response at the bottom here. So it's only possible for clocks to be not synchronized when the two clocks, which are extreme distances apart, appear to be synchronized. There was a reason I put this up here, but it's not clicking with me right now how to digest it. So it's only possible for the clocks to be not synchronized when the two clocks, which are extreme distances apart, appear to be synchronized. Oh, I think the person, this is how I read this. If I want two clocks to not be synchronized from someone's point of view, they have to be synchronized from someone else's point of view. And the idea is, well, that's not always going to be the case. I mean, first of all, make two clocks be not synchronized just by doing a poor job. I could say, you set yours 10 minutes ahead, even though we're in the same IRF. That's not what this person is talking about, hopefully. But it's the case where we know how to compute how much they'll be asynchronous in one point of view, where they're moving with respect to me, when they are synchronous in the other point of view, is the only case we know how to compute. But it certainly is true that if clocks are asynchronous by a certain amount when they're moving by at gamma equals 2, then when they move by at gamma equals 5, they'll also be asynchronous by a different amount in that other frame. So I don't have to know anything about them appearing or actually being synchronized in another frame. It's just that whenever you switch frames, clocks along the direction you're moving are going to be shifted in how much asynchronization there is between them, whether or not you started off with all of them synchronized or not. Okay. That went longer than I thought it was, but I think all those discussions are good, and hopefully they tease out what is sort of intuitively appealing about chapter 7. I mean, I think if you compare all the results, yeah, okay, moving things shrink, that's not, it's mind-blowing if you never thought about that before, but compared to someone's future is another person's past, that sounds on the face of it really impressive. And the more you think about these, the more the three effects really fit together and weave one picture that all conspires to make the speed of light the same in any reference frame. And of course, we've used that in reverse. By assuming the speed of light is the same, we'd be able to derive these three effects. But in any case, you can't just have the length contraction. You need all three effects to make sure that every IRF is going to measure the speed of light the same. Okay, that's the end of chapter 7. We're almost out of time for today, so I'm just going to say, if you want to stay and work on homework, that's great. Tomorrow, I would like you to come and work on the chapter 7 homework, unless you're satisfied and ready to turn it in to me, and you could just give it to me then. I also said in the email today that it's a last call for the chapter 6. I know initially it was due Friday, and then I forgot, so we made it Monday and then Tuesday. So if you don't turn it in right now, or if you're on Zoom and you haven't, I think I've gotten most of the remote people's homework already, give it to me now, because I'm going to post the solutions for chapter 6, and so there won't be any acceptances of it after that. All right. I'm going to leave Zoom open in case any of the three of you who are on there have questions. But as soon as everybody disappears, of course, I'll stop the recording of the video.